Start, sir.
Okay, so welcome back to this last live session on Engineering Mathematics 2. And I did not receive much queries through the link we have circulated, and we have checked on the forum also. So there are as such no queries which I can answer now in this live session. So what I planned, because in other two live sessions I have given some idea or some kind of review of Fourier series, and in one it was on the other basic topics. So today I plan to give you an overview again on this Laplace transform and its application. So this is going to be around 30 minutes and I will be covering including application part. Well, so just to recall, the Laplace transform, or in general when we talk about the integral transform, so it is some kind of integral always you are going to have, which will transform your function. So for instance, here the function is ft, and when we are talking about that we take the Laplace transform of this function, so this function is going to be integrated over this t over the argument of this function. And in this case, in case of the Laplace transform, it is from 0 to infinity, and there is another function here which is called kernel, that is e power minus st. So now when we integrate this function with respect to t after multiplying this e power minus st, so what we will get something function of s. So function of s. So the t is transformed now to the new variable s. So we have a function of t. After this transformation, after this integral transformation, we are going to have a function of s. Well, so the condition here is that this improper integral, because we have the infinity here, so this is an improper integral, and in many cases this improper integral may not converge. So we should have only for those functions, or we can compute this Laplace transform, or we can apply this Laplace transform to those functions only where this integral basically converges. So converges means that this integral should exist, because in several cases this integral may not exist because of this infinity. Well, so we have computed several examples. So for example, one of them was very basic. So the Laplace transform of 1, if you want to compute, so just put there 1, and this exponential minus st will be integrated, and you will get just 1 over s. And this is valid whenever s is going to be positive. So this is what the idea is, that for all s, for all in fact we can take this s as a complex number, and then this integral exists, or this integral makes sense as long as this real s is greater than 0. So we can compute for whatever function given, provided this integral converges. So we need to just basically compute those integrals, nothing else. And the computation of the integral is very easy. So we place here by r, and then compute this integral, which is a proper integral, and later on we take this limit r goes to infinity, and we get this Laplace transform. So here the Laplace transform of 1 is 1 over s, and similarly the Laplace transform of e power minus at is 1 over s minus a, 1 over s minus a. And again here provided, so if we are talking about s is just the real number, then s should be greater than a, or in case we can go for more general parameters, so the real s, that means s we are considering as a complex number, then the real s must be greater than a. So this is another transform. The Laplace transform of this e power minus st is just 1 over s minus a. Well, the important part here is what are the sufficient conditions so that the Laplace, so sufficient condition on our function f, so that this Laplace transform exists, because as I said, there are many functions where we cannot talk about the Laplace transform, because that integral, that improper integral may not converge always. So this is equally important because we should have for the existence that f is piecewise continuous. So that is one condition, that the function which we are taking should be piecewise continuous in this interval from 0 to infinity, and it should be of exponential order. It should be of exponential order alpha, and then the Laplace transform exists. And we also know that this will exist for real s greater than this alpha, where alpha is the exponential order. So what we need basically two conditions, and as written here, these are sufficient conditions. So it does not mean that if these conditions are not satisfied, then the Laplace transform will not exist. So this is not the case. So Laplace transform may still exist if these conditions are not met, but what these conditions say, that if these conditions are there for the function, that definitely this Laplace transform will exist. Well, so this f is of exponential order. What does that mean? If it is an exponential order alpha, that means here, as per the definition of the exponential function, that this absolute value of this function is bounded by this m, some constant time e power alpha t. So this is basically our function is bounded by this exponential function. So if this is the m e power alpha t, and maybe this our function is there, so that should be always below that m1 e power alpha t, which we are denoting here. So this is what we mean by f is an exponential order, and the condition says that this should happen for all t greater than t naught. So there should be some t naught here if it's a t axis, and this is a y axis where f is as given. So here for some t naught greater than so t greater than t naught, this should be the case. It may not be necessarily true for the smaller value of this t, but does not matter, because in this case this piecewise continuity will help us, which says actually that the function is bounded by some constant in any finite this interval. So you take from 0 to t naught, we know that this piecewise continuity will tell us that this ft is less than equal to m2. So these two conditions, the one is exponential order, the another one is piecewise continuity. So these two conditions actually make our function, the function ft, bounded by this m e power alpha t for the whole domain t greater than equal to alpha. You just remember this exponential function is anywhere greater than 1. So if we choose this m here bigger than this m1 and m2, then definitely we can combine these two conditions into one, and we have here the condition finally, which includes the both exponential order and piecewise continuity. So this ft is bounded by m e power alpha t. So these two conditions are needed to basically set our function bounded by m, the constant, times e power alpha t. And once we have that, we can easily show that this integral 0 to r e power minus stft, in fact, when we have the absolute value. So if we have something, if we can show that with the absolute value of the integrand, this integral makes sense, then definitely without that absolute value, this will exist. So here we can assume this has to be a complex number, and then we have this e power s as we have replaced by x plus I y, and then we have t there, and then m e power alpha t dt. So then this m we can bring out, and then we have e power minus x minus alpha t, since this value of this e power I y t, the absolute value, that is equal to 1. So once we have this here, the integral, and this was exactly the idea of exponential order and then of piecewise continuity, so that we can write our function as m e power alpha t, and then we can integrate this easily, and this integral will make sense whenever this x x is greater than this alpha, because then this is positive and then we have a negative number. When r goes to infinity, this will vanish and this integral will make sense. That integral will be bounded by, for all this real s which is x greater than alpha, this integral, the desired integral, the Laplace integral, in fact including the absolute value. So that is always going to have a bigger value of this integral. So if this is bounded by this m over x minus alpha, then definitely that Laplace integral is bounded by something which is m over x minus alpha, and that shows that this is these two, so the piecewise continuity and the exponential order, this is sufficient. So it's not necessary, it is sufficient. Once the condition fulfills, the function fulfills these two conditions, definitely we can say that the value of this Laplace integral exists. And then so as I mentioned before, so the piecewise continuity and this exponential order are sufficient conditions, right? These are sufficient conditions for the existence of Laplace transform and not necessary. So these conditions satisfy. If these conditions are satisfied, then definitely Laplace transform exists. But if these conditions are not satisfied, then Laplace transform may or may not exist. And we have some examples we have done during the lectures which shows that at least one of them was not there. So either the function was not exponential or it was not piecewise continuous. And in those cases also the Laplace transform may exist. But we are not sure. So to make sure if these two conditions are met, then definitely Laplace transform exists. This is the idea of this condition. Well, so and then what is important here, once we know that the Laplace transform exists for those functions, the important part here is the properties. So we have to learn these properties because they help us to find out Laplace transform of complicated functions. And there are many, so I will just review them quickly. So there are shifting properties, which says that Laplace transform of e power at ft. So if we know that Laplace transform of ft is given by fs, then we can compute the Laplace transform of e power at as fs minus a. So there will be just a shift here also. So a Laplace transform of ft minus a ht minus a, and that there is a shift here, and that will be just the Laplace transform one can compute by multiplying this e power minus as to the fs. Fs is the Laplace transform of ft, the same notation. Change of scale property. So if we know that the Laplace transform of ft exists as fs, then we can compute Laplace transform of f at as 1 over a fs over a. And we have the multiplication property. So the multiplication property says that a Laplace of t ft, so when n is 1, but we can work with n, 2, 3, and so on. So Laplace transform of t ft is minus 1, and the derivative of that fs, so d over ds of fs when n is 1. And similarly, we can talk about for n, 2, and 3, and so on. There was a division property which says that Laplace transform of this ft over t is integral from s to infinity fs du, and the Laplace transform of derivative. This is very useful for the application. So when we solve the differential equations, the ordinary differential equations, partial differential equations, then this condition is very much required. And this condition says that the Laplace transform of the derivative. So if you consider n1 again here for simplicity, so the derivative of the first derivative, and when we take the Laplace of this first derivative, so df over dt, then it is simply here s and the Laplace transform of ft, and then we have minus this s and f0. That's all. So and similarly, when we have the higher order derivative, you can again go for the next term till the time you get here this your n is equal to so if for n is equal to 1, you have here s lft minus s0, that is 0, so we have minus f0. When you have n equal to 2, so there will be 3 terms there. So S square Laplace of ft minus S f0 and minus this f prime 0. So similarly, we can go for other higher order derivatives term. The Laplace transform of integral is also useful when we solve some integral equations. So the Laplace of 0 to t f u du. So our function is f whose Laplace transform is fs, but then we can also compute the Laplace of 0 to t f u du, and that is just the fs over s. So you can divide that fs over s. So it's another very important property. And the convolution theorem is also useful in many applications, which says that the Laplace transform of f star g, so the convolution of f and g, this is integral 0 to x, and then you have f x minus t, and then you have f t dt. So such integral, when you take the Laplace of such integral, then it says that the Laplace of ft, Laplace of gt, you have the product there. So Laplace of that integral, the convolution integral, and the result is the product of the Laplace of those two functions which are involved in this convolution integral. Well, and there are two more results which are also used in while solving the partial differential or ordinary differential equations. Those are initial value theorem and the final value theorem, we say. So what are these initial value theorem? It says that the limit you can get as t goes to 0 from the right hand side. So ft, that is nothing but the limit s goes to plus infinity and sfs. And similarly, the final value theorem, so t goes to infinity ft, you can compute by sfs and s goes to 0. So this can be also used in applications. So the idea of the application is to solve the differential equations, and they may be ordinary differential equations, they may be partial differential equations, there may be integral differential equation or integral differential equations, including system of differential equations. So all kind of these differential equations, we can apply these Laplace or the Fourier transform, whatever is applicable. So we consider the initial and the boundary value problem. The problem here is why we go further, or what are the advantages of this applying the Laplace transform. So if we go directly, if we try to attempt or try to get the solution directly of the initial and boundary value problem, so the solution is usually very difficult, and in many cases you cannot in fact perform directly by some other techniques available in the literature. So here the idea of the integral transform, which includes Fourier, Laplace, and the other integral transforms, this problem of the differential equations, for instance, you have you have ordinary differential equation that will be changed to algebraic problem, algebraic equations, or you have PDEs, so that we will get ODEs, and in general the solution of ODEs are simpler than PDEs, and similarly here the solution of algebraic equations are easier than the solution of ordinary differential equation. So these are easy to get these solutions, whether it's algebraic or ODEs, and then we take the inverse transform, because here once we take this transform, then we have a new variable, for instance s there, and at the end we have to write. So here it was a yt, and then we got something ys, and at the end again we have to write yt, the solution of the problem. So we have to take that inverse transform. Similarly, so the idea here is the key steps that we take the Laplace transform both the sides of the given differential equation. So that is common to all kind of the integral or differential equations we are talking about. And then after some very simple calculations, so we have Ly is equal to Fs. So from the transformed equation, so this will be transformed equation. After taking this Laplace transform both the sides, we get L of y is equal to Fs, and then we can take the inverse, because this is the Laplace transform, the simplified form of the Laplace transform of the y as a function of Fs. So in the process here, we may have to solve the ordinary differential equation if you start with the partial differential equations, or if you start with the ordinary differential equations, then we need to solve here some algebraic equations to get this expression of that the Laplace transform of y in terms of some a function of s. And as a final step, which is usually hard to get the inverse transform. So once we have such a Ly is equal to fs, you take the inverse transform and then you get y as L inverse of fs. So this is the solution we have. So in the process, we assume that the solution is continuous and is of exponential order so that the Laplace transform exists. So in all the problems which we have discussed there or will be discussing here, we assume that the solution, the Laplace transform exists to those problems. Well, and so this is the one problem on ordinary differential equation. So we have the double derivative term, first derivative term, and without derivative. And the right hand side, as you see here, a delta function. So delta t minus 3 and h t minus 3. So such kind of problems, it's very easy to solve using the Laplace transform, though without Laplace transform, they may be very, very difficult. Because here, when we take the Laplace transform, both the sides, we know what is the Laplace transform of the right hand side. And that makes life simpler. And the idea here, I mean, this is the property we have used and of the Laplace transform. So the Laplace transform of t minus a and ht minus a. Whenever you have this is a Heaviside function. So the value exists when t greater than or equal to a. So here the formula says that it is just e power minus as and the Laplace transform of the ft. So the Laplace transform of delta there and e power minus 3s will come. So once we take the Laplace transform here, the Laplace transform the double derivative, these are the terms here. So for the double derivative, these are the terms s square ys minus sy0 minus y prime 0, and then we have 2y prime. So we have 2 and the y prime, so you have sys minus y0, and then 2y, so we have 2ys, and the right hand side is just delta. So it's e power minus 3s because the Laplace of the delta function is just 1. So now we are here in the transform domain S, so there is no more t here. And another good point here is that whatever these initial conditions are given, we can directly use at this step. So y0 will be used here and y prime will be used here. So then we have s square plus 2s plus 2 and the ys is equal to e power minus 3s. That is already there on the right hand side. And so this is the algebraic equation we are talking about because we started with the ordinary differential equation. So we have here the algebraic equation, and this algebraic equation can be solved to get this ys in terms of s. And then the final step will be to take the inverse Laplace transform. That means this ys, how to get this yt, you take the inverse Laplace transform. That is also simple. Again, we have to use that property here, e power at. So the Laplace inverse of this fs minus a is equal to e power at ft, e power at ft. And then we have these properties. So the Laplace inverse of this will be just Heaviside t minus 3 e power minus t minus 3 and the sine t minus 3. So that's the solution of the given problem here, of the given problem which we obtained using the application or by applying this Laplace transform techniques. This is like integral equation. So here this is ft and here also ft. So how to solve that integral equation? Again, this idea of the Laplace transform is applicable here. So once we take the Laplace transform, so Laplace transform ft, Laplace transform v power minus t, that is 1 over s minus a, and the Laplace transform of this, that is the Laplace transform of sine t and Laplace ft. So then you take common there the Laplace ft and then simplify this Laplace ft is s square plus 1, s square and s plus 1, and the Laplace ft is then 2 over s plus 1, 1 over s square and minus 1 over s. Well, again, the final step, we need to just invert. So we need to get inverse Laplace transform. So that would be 2 e power minus t plus t minus 1. So this is 2 e power minus t is coming from here. 1 over s square, the Laplace inverse is t, and 1 over s, the Laplace transform is 1, inverse Laplace transform. So once we know the Laplace transform, the getting inverse Laplace transform is not very difficult. And this is the integral differential equation. Integral differential equations means we have differential term, we have the integral term, that is called integral differential equation. And we have this initial condition y0 is given as 3. The idea remains the same, that we apply the Laplace transform. So this is the term from the first derivative. This is 4ys, and then from here we have the 3, and then ys over s, the right hand side again. This is 3, and then 3 over s plus 2 whole square plus 9. And then we have, again, we have to simplify this. And once we simplify, again, we will get this ys is equal to in terms of s. And finally, we take the inverse Laplace transform to get the solution. So to get the inverse Laplace transform here, we need to use some tricks so that we can, we know that whose Laplace transform is this. And the idea is that we rewrite this in this form. And now each of these term, we know already that the Laplace transform a over s square plus a square is sine 80. We know that the Laplace inverse of s over s square plus a square is cos t, and so on. Once we use this formula, we can get directly the solution yt. We can also apply to system of equations. So for instance, this is a system of differential equations, system of ordinate differential equations. x0 is given 8, y0 is given 3. And here the idea is like individually we will apply on each. So this is on x we have applied, then this is on the other equation we have applied the Laplace transform. So we have these two equations, one is on xs ys, the other one is also xs ys, and we have to eliminate one. So either you eliminate first y, y as a function of s, or you eliminate xs, and then, so for instance, if we eliminate ys there, so we will get xs, so we will get the xs in terms of s, and then again here we can take the inverse Laplace transform to get the xt. So once we have the xt, either we directly put it there and get y, or we can again eliminate x this time, and we will get y as a function of s, and then again we need to take that inverse to get yt is equal to 5 e power minus t and minus 2 e power 4t. So another example which includes here that we can also apply to partial differential equations. So this is the example of the partial differential equation. We have the partial term here, del u over del t, we have del u over del x, we have right hand side as x is greater than 0 and t is greater than 0. So, and we have these following initial and the boundary conditions. So we can take the Laplace with respect to t, though in this problem we can also apply the Laplace with respect to x, but with respect to t it's going to be easier. And once we apply with respect to t, then this will be the result. And now here we can use directly this initial condition, which is given here as 0, and then we have a differential equation in this capital U. We have differential equation. Earlier we were getting just the algebraic equation, and then we could easily get that u in terms of s, but now here we have the differential equation, so the ordinate differential equation. So this is a linear differential equation we can easily solve indeed. So the solution of this differential equation will give us again this uxs in terms of s. And there is a constant again here because we have integrated this, but we have not used the other boundary condition. So once we have this, we can use provided this the given boundary condition. There's u at x equal to 0, t is given as 0. If we apply the Laplace transform here, we will get u0 as equal to 0, and that can be used there to compute that constant, which is coming to be 0 in this case. And finally, we have the u in terms of the s. And then we can take the Laplace transform again. So uxt is x e power minus t. So the idea whether it's a differential, it's a partial differential equation, it is an ordinary differential equation, it is a integral differential equation, or it is a simply differential equation or integral equation, whether any type of integral, any type of these equations, differential equations are there, we need to just apply the Laplace transform, use appropriate initial boundary conditions there, and then either we will get algebraic equation or we will get the ordinary differential equations. We can solve for the variable, the transformed variable s, and then finally we need to invert it to get back to the original solution. So this is what the idea of the application of the Laplace transform. We have a nice application. So with this, I thank for joining in this live session, and that's all. So wish you good luck for this course. Thank you very much.